job. You should be really proud of yourself. So you can be ln of like 17 factors.
Did I start that? I think I did.
13 now.
Nav is playing. Yeah.
I can do it quickly. All right, everybody good with that? So I will admit, the order of the reaction, that exponent n, and we've done a lot with order already, but I haven't really given you the full scope of what order really means. We're finding it. We did 3 graphs in this lab, and we're determining that, okay, the lab is either 0 first or second order. I almost said which one it was. But the actual meaning of the order is still yet to be uncovered. So do know that. If you're thinking, okay, so I can find order, but I really don't know what it does for us or what it is, that's still to come. Don't forget, by the way, you have a reading quiz tomorrow. The reading quiz tomorrow is on the mechanism of reaction. This is going to be something that's new, but I don't think it's terribly heavy. I think you'll be able to read through it and say, yeah, okay, we can do this. All right, just one other slide with a few things about finding a differential rate law, then we'll do an example. So this is the same thing as what we started with on the last slide. If we want to find K, the K value, we first have to figure out the rate law by finding the order of the reactants, and then choose any trial that you're given from the data and plug the rate and all the concentrations in to the rate law and just solve for K. And again, I know that seems like it's difficult, but when you really do it, it's really easy. Just plugging numbers in to a formula and solving for an unknown. Now, I know that we had talked about the unit on K. We kind of derived how we figure out the unit on K with the with the integrated rate law. Do know that the unit for the rate of a reaction is always going to be molarity per second. Rate is always something changing per second or per time. So in this case, the rate of a reaction is going to be molarity per second. Now, I promised you, I didn't promise, but I told you, which is good as a promise, that I wouldn't derive anything, Samir. So what I would just suggest is you don't write all this out. I would just say, write down first order, the K unit is going to be 1 over seconds, inverse seconds. And if it's second order, the K unit is going to be 1 over molarity seconds. What I did in the couple lines before that was I kind of derived how we get that unit. But if you just have what the unit on, really pretty much you can figure out the K unit every time. It's just kind of part of it. I wouldn't suggest memorizing the unit on K because it's different for every order. Go ahead.
You know how you said like plug in the rate and the
yeah, to find the K, yeah.
So like would the rate just be, for example, if I like pick like 10 seconds or something, like the molarity at 10 seconds, like for instance?
No, we're not dealing with time with the differential rate law. It's all just about concentration and rate.
But like is the rate like gonna be like a x value of the graph? Like,
There's no graphing with the differential rate law. So it's totally different. The integrated rate law you use the graphing for. The differential rate law, you're just going from values on a table.
Wait, but do we have like the data table? Like we get the data table.
Yeah, you'll get the data table.
So like it would be like
Yeah.
rate and then molarity, right?
Yeah,
We just pick one.
yeah. How does the molarity affect the rate? That's all it's about. Yep.
when you're finding order, do you do it just to one of the rates, one of the stages?
No, you have to find the order of each reactant that it gives you. And we'll walk through one of these. I'd like to do just number one with you. Yeah. Oh, you will see that too. I'll show you. Just waiting for everybody to finish. I told you not to write the whole derivation. You didn't? We good? Still writing? Nobody? Okay. Let's do this, this number one. So the first thing we want to try to do, well, I guess we can answer. I'm just going in order of the questions on this. Let's take a look at number one. The chemical equation first is right at the top. We have two reactants. HgCl2 is reacting with the oxalate ion. It looks to me like a redox reaction. Look like redox to you?
Sure.
Thought so. Okay, so there's two reactants and three products in this problem. Remember, the rate is always defined by what the concentration of the reactants are. So since we have two reactants, what happens is several trials are done. That's what the data table is. There's 4 trials that are done, and the concentration of the reactants are varied. So that sometimes they're 0.1, sometimes they're 0.2, and then it varies those. In order to find the order of the oxalate ion, I chose oxalate first, even though it's the second reactant, because trials 1 and 2, the first 2 trials of this thing, notice what happens with the HgCl2. It's held constant. So the rate is not changing because of HgCl2. It didn't give it a reason to because it stayed constant. However, the C2O4 doubles. See it? It goes from 0.1 in trial 1 to 0.2 in trial 2. So when the concentration of C2O4 doubles, what happened to the rate?
Quadruple.
It quadrupled, right. From trial 1 to trial 2, the rate has quadrupled. It's gone up by 4 times. So what does that say about the order of C2O4? Yeah, it's second order. That's why we have to run multiple trials. We've got to have a couple of trials where one of them is held constant, the other one changes. We see what happens to the rate. Then the second one has to be held constant, where the first one changes. We see what happens to the rate. Yeah.
Right, so does that, for the second order, doesn't mean that like you double something, like, is that like an hour thing?
Yeah.
Okay.
Yeah.
Is the one before that just linear, like you multiply by 2, multiply by 2?
Okay, so the oxalate we decided is second order because when we doubled its concentration caused the rate to quadruple. And I chose trials 1 and 4 to find the order of HgCl2 because the concentration of oxalate is staying the same from trial 1 to trial 4. I'm ignoring 2 and 3 altogether right now. And notice the HgCl2 is doubling. It's going from 0.1 to 0.2. When the HgCl2 doubles, what happens to the rate? It doubles as well. It goes from 1.3 to 2.6 times 10 to the negative 7. So that tells us that HgCl2 is first order.
Yeah, how did you figure that out? I'm not sure.
Oh yeah, see how the concentration doubles?
Oh,
and then from 1 to 4, the rate is doubling.
Why can't you pick like when it goes from 0.1 to the first one?
Yeah, like in trials 2 and 3?
No, in
No,
trial.
he's saying could you use 1 and 3?
You don't want to, because from trial 1 to trial 3, both reactants are changing.
Oh, so you have to use it only.
Yes.
Yeah, try to hold one of them constant, and then just see how the other one affects the rate.
Oh, that's.
Yeah, we want to try to minimize the number of variables in there,
Thank
if
you.
we can. Yep. Now, we haven't talked about this because with the integrated rate law, all we've dealt with is one reactant. Like in the lab, we only looked at the food coloring as a reactant, and we found the order of the food coloring. There was bleach as the other reactant, but we didn't look at bleach. We did the food coloring because it's the food coloring that changes and its absorbance changes because it was colored. In this case, though, since we have 2 different reactants, we can find the overall order of this reaction. And the overall order, you would just add the 2 orders together. So this would be overall a third order reaction. Now again, as I said at the beginning of the hour, we haven't fully learned what the order really is yet. I would just tell you this. Just because this is a third order reaction does not make it a fast reaction. The order does not tell us how fast it is. What does tell us how fast the reaction is?
The rate.
The rate, or the value of K. The value of K is going to dictate how fast the reaction is. If K is big, the reaction is going to go fast. The order is going to mean something. In fact, normally when the order is high, The rate is slow. It's a slow reaction. And we'll talk about why that is. But not yet. Okay? Take a look at question B. Question B is, write the rate expression for the reaction. The rate expression is just the same thing as the rate law, the differential rate law. Okay? It's also called a rate expression. So that question is super easy because we already have found the order of the two reactants. So all we have to do now is, we know the pattern for differential rate law. It's always rate equals K, get the K in there, don't forget the K, times the concentration of the first reactant, HgCl2. I'll just do them in order of the way they showed up in the chemical equation. That was to the first power, that was just order. And that's times the oxalate concentration to the second power. That was its order. That is the rate expression, also known as the rate law, differential rate law. Yes?
I don't know if you said this earlier, I in the packet.
You can, yeah, you can, we'll just mark up the packet as much as you want. Yep. Yeah, again, I'm not collecting that thing, it's just so we can have some examples to do together. So that's it for A and B. Part C, calculate K for the reaction. Now I asked you to take some notes on the K. Look back at what you wrote down. To find K.
Find the order first.
Okay, we did that.
Choose one trial. Plug in rate and molarity of A and solve for K. Gotta fix this.
Yeah, that was great. Which trial would you like to use if we have to plug some numbers in? The first one, because the numbers are so simple. Yeah, that's what I always do is when I need to choose one trial to find K, look at their trials and see which trials have the nicest number. We could do one without a calculator, so let's do number one. So, okay, for trial one, now this is our rate expression. In trial one, we know everything except for the K. And the K is a constant value. As long as the temperature stays the same, it's going to be the same for all four of the trials. Every time you run this thing, the K is going to be the same, as long as we're at the same temperature. So the rate was 1.3 times 10 to the negative 7 molarity per second. I'll go ahead and put the units in here so we can see what the unit on K winds up being. That's the rate, that's this thing right here, equals K, we don't know what that is yet, times the concentration of HgCl2, 0.10 molarity to the first, times the concentration of C2O4. In trial one, it was 0.10 molarity, and then it was to the second. We're solving for K. What is 0.1 times 0.1 times 0.1? That's what we have over here. Yes, 0.1 to the third, also known as 10 to what power?
10 to the third. 10 to the negative third.
Negative third, right. Because this is 10 to the negative first, raised to the third power, 10 to the negative third. You with me? So, divide out the 10 to the negative third, because we want to try to get K by itself. So K equals this divided by 10 to the negative third, which is, don't get this wrong.
1.3 times 10 to the negative 4.
Negative what?
Negative 10.
Oh, you got it wrong. You went the wrong way on it. That's what I was afraid of. And then you repeated it wrong? Okay, 1.3 times 10 to the negative 4.
Well, I thought I said that first.
I didn't hear you the first time, but you had to say it loud.
Oh, then I.
Okay, now what's the unit? Notice over here the unit is molarity times molarity times molarity. You got molarity cubed over here, yes? This side over here was molarity per second. So if we have to find K, we got to divide out the molarity cubed, yes? And what does it wind up being?
1 over molarity squared.
Yes, 1 over molarity squared seconds. 1 over molarity squared seconds. Ah, it all kind of runs together. I'm sorry about that. I'll write that nicer. If I can just clean that up. There, it looks like that. Yeah, take a look at that unit again. This is molarity cubed over here. So if I need to get K by itself, I got to divide out the molarity cubed. I already have 1 M on top. I got 3 M's on the bottom. So just cancel 1 out, and we'll have 2 M's still on the bottom. Yes? So as the order goes up, the more molarities in the denominator you have. Did you catch that with... Oh, I passed it. First order, we didn't have any molarities in the bottom. Second order, we had one molarity in the bottom. Now we've got a third order reaction. I've added them together. And now I have two molarities in the bottom. Yeah.
Wait, is the multiple choice for this test like mostly conceptual?
There's some of everything. There's some problems to do. Yeah, the numbers would be nice. This would be good. I mean, we've been able to do all this without a calculator so far. This would be good. In fact, I think this question was taken from an AP exam. Yeah. Okay, now let's just do a D, and then we'll be done. And D is so easy. My goodness, it's almost insulting. When the concentrations of both the mercury 2 chloride and oxalate are 0.3, what is the rate of the reaction? Now that's not on our data table. We never have 0.3 for concentration. But what if the concentration of this is 0.3 and this is 0.3? You just use, still using this reaction rate law. So we want to find what the rate is. Well, that's what this question is asking. What's the rate? If this and this are both 0.3. Well, now we know K. We can plug in that number for K. We plug in 0.3 for this, 0.3 for this, yes? And that's it.
Wait, would it be 3.9 times 10 to the
Have you done that already?
No, I'm just wondering, because like, I looked at the table and I'm like, when they're both 0.1, it's 1.3 times 10 to the negative 7. When they're both 0.2, it's 2.6 times 10 to the negative 7. So like, I thought...
Be careful though, because one of them is being squared.
Oh.
So I don't think you can just assume that. I mean, just be careful.
Oh wait, yeah, you're right.
So anyway, to find that, you're just going to take the rate. You're going to plug in the K value, 1.3 times 10 to the negative 4th. And that's 1 over molarity squared seconds. Then times 0.3, that's the concentration of HgCl. I'm just using this rate law, plugging the numbers into it, to the first, times concentration of oxalate, 0.30 to the second. I forgot to give that a unit. I'll put an M down there. That's it. Find the rate. You're putting 3 numbers in and multiplying the 3 numbers. It's not hard. These are nice problems. Now, does it get harder than this? Yeah. But you know what? Even when it gets harder, I don't think it's terrible. I think this is a nice chapter. Especially after the thermal chapter, which is kind of hard. This one, last year, I don't think we had a curve on the test on kinetics.
We did it?
I don't think there was a curve.
Oh
It's
my
literally
God.
2.3 less than last time.
But on thermal,
The
they
whole
had a 9-point curve.
Oh, is there another
9.4.
fundraiser coming up?
2.5. That was very good.
What's Regan?
I was
We
sad.
should make a charity and then make
I was
Mr.
really
Moore
sad.
donate just so we can have a goal and get extra.
I haven't heard anything about the winning classes either. I bet we won, or we were one of the top.
Oh, I didn't know there was a winner.
I think they had.
would've donated.
I think they were going to
more
get
if there
pizza
was
for
a
the top 5 classes. I'll bet that we were one of the top.
winner. Can we donate
Was
more
it
money
3?
now?
You told us that.
No.
Yeah, I like
I think somewhere along the line I heard it was 5.
I like
5 classes.
winner.
So, but I haven't heard anything. Nobody ever said anything after that week.
HCl.
All right.
So funny.
So,